Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020. This is the conclusion of the lecture entitled Improper Integrals. So previously we learned with Simpson's rule and the trapezoidal rule how to address a definite integral when we couldn't find the antiderivative, and we also talked about what happens if this interval here is infinite. But what we haven't addressed is the situation where you have a discontinuous integrand. And so we're going to talk about that here in this lecture. So if f of x is continuous on the interval closed a, open b, but not continuous at b, then the definite integral from a to b, f of x dx, is equal to the limit as t tends to be from the left of the integral from a to t, f of x dx, provided the limit exists and is finite. And we do need to use a left-handed limit of that because the interval of integration is entirely on the left of the upper limit. Similarly, if f of x is continuous on this kind of open-closed interval, but not continuous at a, the definite integral from a to b, f of x dx, is equal to the limit as t tends to a from the right of the integral from t to b, and you see that that's what we would want to have too. Now, if f is not continuous at a point c in between a and b, you break it up into two integrals, and if both of these integrals are convergent, then the integral is convergent. You'll handle the c in the same way that you did in number 1 and 2 above. And suppose that, finally, f of x is not continuous at x equal a and x equal b, then you will have to, again, break it up and look at the limits. So, again, in cases 3 and 4, both of the integrals have to be convergent for the integral to be also convergent. So here's an example for you to try. Determine if this integral is convergent or divergent, and if it is convergent, find its value. So we're integrating from 0 to 3, 1 over the square root of 3 minus x. We usually start by thinking about, well, what's the graph of this like? And you see that this goes off towards infinity when x is equal to 3. So that's where we're going to have to put the limit. So the calculation then will go as follows. The integral from 0 to 3 of 1 over the square root of 3 minus x dx is equal to, we take the limit as t tends to 3 from the left, the integral from 0 to t of 1 over the square root of 3 minus x dx. Now you guys should be experts at computing these integrals now, so you realize that that's going to be this expression that's going to be evaluated at t and 0, and we're going to take the limit as t tends to 3 from the left. Come down here, we do that, and t tending to 3 from the left, what we'll have, this second term will be 0, so the answer is 2, the square root of 3. So you see this is a convergent integral, and that is its answer limit. Here's another one. Determine if the following interval is convergent or divergent, and if it's convergent, find its value. So we're integrating from minus 2 to 3, 1 over x cubed dx. Well, again, the graph tells us much, and between minus 2 and 3, there's this infinity business happening, so we're suspicious. So what we need to do is break this into two integrals, going from minus 2 to 0 and from 0 to 3. Now, both of these integrals have to converge for the sum to converge, so let's just start with the one that is the definite integral from minus 2 to 0 of 1 over x cubed. So we do the calculation here, and we find out that this is the limit as t tends to 0 of this expression. That becomes negative infinity. So the answer is this diverges since one of its components diverge. Another problem. Determine if the following integral is convergent or divergent, and if it's convergent, finds its value. So the integral from 0 to infinity of 1 over x squared dx. And again, we're going to look at the graph briefly, and we see what's happening. And so we're going to break this into two pieces. We're going to go from 0 to 1 and from 1 to infinity. Now this one, from 1 to infinity, was one of the very first ones that we talked about. We learned that that in fact did converge. But we have to think about the other one. Now the other one is of the second type that we've been discussing now, because it's discontinuous at 0. So this is a limit as t tends to 0 from the right of the integral from t to 1 over x squared dx. We do the calculation. Again, you should be good at this, and we find that this is infinite. That means it diverges. Now, you might say, this is interesting, but are there any applications? And of course there are. And the application I'm going to talk about has to do with probability theory. So every continuous random variable has a probability density function f of x. And the definition of probability density functions are that they have to be positive or 0 for all x. And when you integrate them from minus infinity to infinity, you get 1. And moreover, the probability density function can be used to determine the probability that a continuous random variable lies between two values a and b. So the probability that x is between a and b is given by the definite integral from a to b of f of x dx, where f of x is the probability density function. So here's an example. The probability density function for the weight in line at a counter is given by this function. Notice that the probability that you weight less than 0 in a line is 0. But other than that, you have probabilities of weighting, and t is the number of minutes spent in a line. So you're answering each of these following questions. First of all, we want to verify that this is a probability density function. But then, after doing that, we want to determine the probability that a person will wait in line for at least 6 seconds. And at least 6 minutes, rather. And at least 6 minutes is 6 or longer. And this is what the function looks like. And you see the probability of having to wait a long time goes down the longer you make the time that you're looking at waiting. Okay, so first thing, we're going to integrate this from minus infinity to infinity. And notice that since the function is 0 when you're less than 0, this integral only is from 0 to infinity. So this is an improper integral. So we take the limit as u tends to infinity. This is the integral from 0 to u. There's our integrand. We've done this before, so you find the antiderivative, you plug the values in, and you take the limit as u tends to infinity. Now as u tends to infinity, e to the minus u over 10 approaches 0, so this indeed is 1. And it's also greater than or equal to 0. We saw that from the graph. So now we're going to determine the probability that the person will wait at least 6 minutes in line. So we're saying the probability that x is greater than or equal to 6 is the improper integral from 6 to infinity of that density function. And then we're taking the limit as u goes to infinity again. And we calculate it, and we get that the answer is going to be e to the minus 3 over 5. But if we plug that into a calculator, we'll get that it's a little better than 1/2. In closing, now, more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.